Okay, so now we have the warm-up for 1-5. Please go ahead and pause it and give students about 5 minutes to work on this. Okay, so we're going to go ahead and start off with the subtraction of the two functions. So I'm going to go ahead and I'm going to take my first function, 3 minus 2x, and I would subtract the second function g of x. And then, because it says 4 here, that means I'm going to plug 4 into wherever there's an x. So this turns into 3 minus 2 times 4 minus the square root of 4. And then I simplify as much as possible. So 3 minus 8 minus 2 gives me negative 5 minus 2, which is negative 7. And there's our solution. Okay, for our next one, we're finding f times h at 1. So I'm going to take my function f. I'm going to times it by my function h. And then I'm plugging in 1 into the x spot. So this is really now 3 minus 2 times 1. 3 times 1 squared plus 2. And then we'll go ahead and work those out. So we've got 3 minus 2 times 1. So 2 times 1 is 2. 3 minus 2 is 1. So that gives us 1. 1 squared is 1. Times 3 is 3. Plus 2 is 5. Which gives us a solution of 5. Okay, our next one is our composition. So g composed with f. So f is second, so that's getting plugged into the g. So that means this is going to be square root of x, but instead of x, we're plugging in that f of x. So 3 minus 2x. And then because of the negative 2 here, we plug in negative 2 into the x spot. So this is square root of 3 minus 2 times negative 2. And this negative 2 times negative 2 becomes 4. So it's square root of 3 plus 4, which is square root of 7. And that's our solution. Okay, so that's a review of some of our function operations. And now we're going to talk about the very last section in Chapter 1, and that's the inverse of functions. So students will be able to determine if a graph has its inverse, and then also be able to find the inverse. Now an inverse is formed when the values of the domain are interchanged with the values of the range. That means we're switching our x and y's around. So in an informal look at inverses, so if I have the function f at x equals x plus 4, I can create a table for it. I can plug in 0 for x, so 0 plus 4 gives me 4. I can plug in 1 for x, so 1 plus 4 gives me 5. And then I can plug in 2 for x, 2 plus 4 gives me 6. And we kind of get the idea here. Now what ends up happening for our function is I have these coordinates 0, 4 and 1, 5. And then 2, 6 and 3, 7 and 4, 8. And when I graph it, it's going to look like this. So I'm starting at 4, going up 1 over 1. Okay, but for my inverse, I'm switching that x and y around. So I'm taking each coordinate and I'm flip-flopping them. And so now this looks like 4, 0 and 5, 1 and 6, 2 and 7, 3 and 8, 4. And because these x and y's are being switched around, what's really interesting is your graphs are symmetric. They're actually reflected over this line y equals x because they have been flip-flopped around. And so to be able to find an inverse, if I rewrite this y equals x plus 4, I can actually switch those around and solve for y. And that gives you the equation of my inverse. And you can tell that's probably what my graph would look like if I could draw a straight line. Yeah. And so that's what we're going to be talking today about, is being able to create that inverse. Does something have an inverse? Because some things will not have an inverse. So we're going to find the inverse of y equals 4x. So again, over here, to find the inverse, we switch x and y and solve for y. So I flip-flop those. And now I'm going to solve for y. So I have to move that 4. And so now I get that equation y equals x over 4, or 1/4 x. Now we can verify that things are inverses by doing a composition. When we do a composition, we should end up with the value of x. And we show composition in both ways to show that it works out. So if I want to do f of g of x, assuming that this is my f and this is my g, then I'm going to go ahead and plug the g into my x position. And what happens here? 4 times 1/4, well, those 4's cancel, giving me 1x, which is really just x. So that shows that they are inverses. We have to check the other way too. We check the g f of x. And so now we have 1/4 of 4x. Again, those 4's canceling, giving us 1x, which is really just x. So now we have verified that they are truly inverses. And just a little reminder about yourself, when you describe the graphs of inverses, they should reflect about the line y equals x. And a function must be 1-to-1 to truly have an inverse. So you're going to start finding graphs like this aren't considered 1-to-1 because they don't pass what we call the horizontal line test. So we have to restrict the domain to be able to have inverses. So now we may truly only look at this part of the graph and restrict the domain to x is greater than or equal to 0. So that way I can truly have an inverse now of that function. Okay, so let's go ahead and look at how these graphs look. So y equals 4x. So I start at 0. I go up 4 over 1, up 4 over 1. And then we have that inverse. Start at 0, 0, go up 1 over 4, up 1 over 4. And then again showing you that that line y equals x gives you that mirror line where the two graphs mirror each other each side. You could fold on that and they would match up perfect. Okay, so we're going to go ahead and practice verifying some inverses. So we've got the function f of x and g of x. So I'm going to go ahead and do the composition where I'm plugging g of x into f of x. So this is 2, and in the x spot we're going to put in that g function. Now luckily we have that cubed root, and the cube should cancel each other out. So now I have 2 times x plus 1 over 2 minus 1. The 2 should cancel each other out. So now I have x plus 1 minus 1. The 1's cancel out, giving me x. So first step of verification done. So now we're going to do the composition the other way. So now I'm going to have that cubed root And in that x spot, we're going to put 2x to the third minus 1. And then I continue on with the function. So now inside of that cubed root, the 1's are going to cancel out. So now we have the cubed root of 2x to the third over 2. The 2's cancel out, giving me the cubed root of x cubed, which those cancel each other out, leaving us with x. Now we don't have to worry about any sort of restrictions working with the cubed root, because you can take the cubed root of a negative number, you can take the cubed root of positive, you can 0, and a cubed function is a one-to-one function. And that's not a very good top to my cubed root. But it does pass the horizontal line test. Even when it looks like it's sort of kind of getting flat here, it still passes that horizontal line test because there is just enough of a change. Okay, so now we have the function f at x is 5 over x minus 2, and we're going to try and figure out what the inverse is. So the first thing I'm going to do is I'm going to go ahead and rewrite this as y equals 5 over x minus 2. And then I'm going to switch those x and y's around. So now I have x equals 5 over y minus 2. And what I'm going to go ahead and do is I'm going to go ahead and put this over 1, and I'm going to cross multiply. So just because I find that easier. And I have x times y minus 2. And that's because I needed that y to come up on my equation so I could solve for it. So now I'm going to divide by x. So now I have 5 over x equals y minus 2. And then to get y by itself, I add 2 to both sides. So now I get an equation of y equals 5 over x plus 2. So it looks like this is the inverse of our function. And we have several things that we have to be careful of. In our original equation, we have x can't be 2. And in our new equation, we have x cannot be 0. So some restrictions to think about there. Okay, a function is one-to-one if, for a and b in its domain, the function at a equals the function at b implies that a equals b. That means that I can only have a y value popping up once for each one. So in our parabolas, when we start seeing, we've got a 1, 1 and a negative 1, 1. We've got that y value listed twice, and so that's where we get this whole idea of a horizontal line test to tell if a function is one-to-one. And we can do that, so the horizontal line test, if it's always increasing over the entire domain, like a cubic function, or if it's decreasing over the whole domain. So that could be a flip-flopped cubic function. So the first question is the function f at x equals a square root of x plus 1, 1-to-1? So if we were to graph this, we could do a table, we could plug this into our calculator to get an idea of what this looks like. We should also be able to use our transformations to know that this is a square root function moved up 1. So I can move it up 1, there's our 0, up 1 over 1, up 3 over 1, up 5 over 1. And using our horizontal line test, this would look like a one-to-one function. Okay, so let's move on. Steps for finding the inverse. Check to see if the original function is a one-to-one function. Then you can replace your f of x with y, flip-flop the x and y's, solve for y, and then this is our notation for an inverse. It's f -1, so that's the inverse notation. And then verify. So we just double check that when we do that composition that they're both equal to each other, or they cancel each other out to get x. So find the inverse of f at x equals square root of 2x minus 3. Sketch the graphs of the two. So I'm going to go ahead and I'm going to rewrite this y equals square root 2x minus 3. I'm going to flip-flop. And now I'm going to try and get y by itself. So the first step is getting rid of the square root. So I square both sides. And that should cancel out that square root. So now I have x squared equals 2y minus 3. And now I'm going to move that 3 over. So now I have x squared plus 3 equals 2y. And then I get rid of that 2 by dividing. Now my problem here is that when I graph this, I'm going to end up with only half of a sideways parabola because of that square root. Because I can't square root the negative numbers. So when I'm looking at this parabola, I have to be careful because I only want this part of my parabola. So I've got to start thinking about how is this domain now affected to truly make it so it is only this half of the graph. And so I want to think about where is the center of that. So that's where we're going to go ahead and pull out our graphing calculator. So we're going to go ahead and look at that. We've got our square root 2x minus 3. We've got our x squared plus 3 divided by 2. We're going to go ahead and look at the graphs. And we see that square root. And then we see that parabola. But notice that it's not a true reflection because we really shouldn't have this bit right here. So we got to look at how that vertex is right here, and we're cutting it off just like this graph is cut off here. So our domain should be x is greater than or equal to 0. And so when we're doing these and we're looking at the square roots versus the squares, we have to be cognizant of this restricted domain. And so when we're sketching, we're looking at that whole, showing that this is our f at x and this is our inverse. Showing that it's truly reflected over that y equals x line. And that's the idea, that's the whole idea behind the inverses. So we need to be aware of that. Okay, so practice show that f at x equals 2x and g of x equals x over 2 are inverse functions. So we're going to practice that by, to prove or verify that they're inverses, we do the composition. So we're going to go ahead and start with plugging g of x into f at x. Showing that those 2's cancel, leaving us with x. And then we do the composition the other direction. So we're plugging the f at x into, so 2x over 2, letting those 2's cancel. So we have verified. Okay, is the function 1-to-1? So this is a really good time to practice graphing and looking at it. Almost all lines, unless they're a constant function, all linear, true linear, not the constant ones, but the linear functions, are going to be 1-to-1. So when I'm looking at this, starting at 3, going down 1 over 2, down 1 over 2, yeah, it would pass that horizontal line test just fine. So yes, this is 1-to-1. So our next one is kind of tricky. We could do a table of values, or we could pull out the handy dandy calculator and take a good look at what this looks like. So I'm going to go ahead and we're back to that graphing calculator and clear out my functions. And we're going to go ahead and do x squared divided by, and then on the bottom we want x squared plus 1. So see how I'm putting that whole thing in parentheses because I want to make sure that whole thing gets on the bottom of our fraction. And then we're going to go ahead and graph that. Interesting. So when I'm looking at that, that does not look one-to-one. It looks like if I were to draw a line across right there, that I'd get similar values. So I can check my table just to make sure. And yep, I'm seeing some mirror imaging here, the 0.5, the 0.5 double y values, which tells me that this is not a one-to-one function. So I'm just going to take a quick snapshot of that. And then I'm going to look at that graph, take a quick snapshot of that to show us that that is not, definitely not one-to-one. So if you're not sure by looking at the graph, like that there could be some change in values and stuff, and it looks like it might. If you're really unsure, take a look at these tables and look and see if you get some double y values popping up, and that'll tell you right away that it's not a one-to-one function. Okay, so let's find our inverse. We have y equals 5x minus 7. We flip-flop. We solve for y. And there's our inverse. Now to write it in function form, we take our function inverse, and then we just rewrite our expression. Okay, so that's pretty much inverses right there for you. Your assignment, 4 through 60, every fourth problem, then 63, 69, 74, 80, 85, and 97. So the next time we meet, you're going to have your review. The assignment is to work on that review, get as much done as you possibly can. So then the next time we meet, we're taking care of last minute questions. You got a really good study guide to help you for your test.